Welcome to an ultralight design video from the Ultralight Airplane Workshop. We're continuing our series on the design of the UWS-4 ultralight airplane. In this video, we're going to talk about how to make smooth drawings. Drawings that don't have abrupt edges in them or odd bulges, and drawings of surfaces that you might be able to want to wrap in something like aluminum sheet without having to have complex curves. If you've been watching this design series, you know we've been using a book by Dan Raymer called Simplified Aircraft Design for Homebuilders. Now this video covers the entire chapter on drawing that is in Dan's book. Well, let's get started. This is another one of those times where Dan is going to cover a whole lot of really interesting information in his book that we're just not going to use here in our build. And in this case, it's really because Dan's really covering more doing pencil and paper drawing. And as you've known, if you've seen some of our past videos, we're really using OpenVSP to do the basic drawing or the basic configuration, the basic layout of our airplane. Now, when we finally move to CAD to start doing some of our drawings for parts, we're going to export what we've done in OpenVSP and put it into CAD. So we probably won't do any hand drawing. I will say that there has been an exception to this. Early on, when I was thinking about how do I want to do some of my hinges, at lunch one day, I did do some drawing in a notebook on how I might want to try to do hinges. But other than that, there hasn't been any hand drawing on this project. Now, once again, the fact that Dan covers some really interesting information in his book is probably a good idea to at least think about or look at or investigate Dan's book. If you want to do that, there's a link down in the description that will take you to a page on the Ultralight Airplane Workshop's website, and you'll see a link to this book and to some other books that I use in my design process. Now, since Dan covers mostly line drawing in his book, and I've been using OpenVSP, you might think, well, what in the world are you going to talk about in this video? Well, Dan does make some really interesting points that I think is still applicable even though we're using OpenVSP. And so that's what we're going to talk about here in this video. I think we'll probably skip doing an overview of what we did in the last video. If you'd like to see that video, I'll put a link up here in the upper right hand corner you can click on, and it'll take you to that last video that we did in this series. Dan covers four major sections in this chapter of his book. One is conic lofting, which is basically making curved lines that would be a conic as though you had cut a cone with a plane and the outline on the outside edge of that cone where the plane cut it. That's called a conic shape. So that's one way of making fairly smooth, fairly nice lines for something like an airplane fuselage. Another one is Flatwrap lofting. That's making drawings where you can actually wrap it with something like sheets of paper, or in our case, it would be something like sheets of aluminum without having to do complex bending of the aluminum. You only have to bend the aluminum one way. Then he talks about wing and tail lofting, and actually flat wrap lofting has something to do with that wing and tail lofting. And then he talks about measuring what you've drawn, because you want to be able to have some information about what you've drawn. For example, wetted area, surface area, volume, because you're going to need those for making some estimates later on, like the weight of your airplane. So we're going to cover these four sections in Dan's book. And as we're going along, we'll talk a little bit about what we've done different using OpenVSP. So the goal of the conic lofting is to make a continuously smooth surface, a surface that's aerodynamic. Now this conic lofting, the way Dan describes it, is generally used when you're doing drawing by hand. And if you want to know more about how to do this conic lofting by hand, go ahead and get Dan's book and read it, because it's a very interesting method. And if I was doing drawing by hand, I think I really would use this because I really like it. Now, if you're using CAD, most CAD tools already have built into them nice methods for doing smooth sides and curved 3D objects. Things like splines. Now, you may not necessarily get a conic loft, but you can still achieve the same goal of getting nice, continuously smooth surfaces. And then, like we're using on this project, the UWS-4, we use OpenVSP. Now, it has a slightly different method of making smooth sides than you'll generally find in CAD lofting, but I think it still does a pretty darn good job of making smooth surfaces, as long as you know how to use it. Now, in previous videos, I've talked a lot about how to use OpenVSP for making smooth surfaces, and we'll do a little more about that in this video. And the way I generally am making my smooth surfaces, excluding wings or wing type surfaces, is I use something called the stack or the fuselage. And then within the stack of our fuselage, in the dialog window for configuring them, there's something called the Skidding dialog. And this is really what you would end up using to control the smoothness of your surface. But contributing to how smooth that would be would also be in the cross-section tab. We'll talk a little more about that here in a moment. Now, there are some other objects in OpenVSP that always has a smooth surface. That would be a pod, an ellipsoid, and a duct. Now, I shouldn't say necessarily aerodynamic. For example, an ellipsoid would have a trailing edge that's not very aerodynamic, although it would have smooth surfaces. Now, a wing will generally always have a smooth surface just because your airfoil will generally have smooth curves. Almost always has to have smooth curves in order to be aerodynamic and have low drag. Now, that's in the chord direction. Now, in the span direction, it may or may not be smooth, but you don't necessarily have to have it be smooth just because of, for example, changes in dihedral. Now, the plan form, the outline of it as you're looking at it from above or from below, can also have smooth curves to it. And the way you get that is with the Modify tab. And we've done that quite a bit when we're working on both the wing and the tail on the UWS-1 project. And then one more way of getting smooth curves is with the body of revolution, but whether or not that's smooth kind of depends on what cross-section you use. For example, if you use just a rectangular cross-section, that would not be very smooth. But if you use something like an ellipse or an airfoil, that would be smooth. Now, the thing that I spend, it seems like the most time on when I'm trying to smooth stuff is the fuselage. Now, OpenVSP does have an open fuselage type. I think I'm starting to like the stack a little bit better, so let's do that. There's a lot of similarity between the fuselage and the stack. So here's what the default stack looks like. Now, if you kind of ignore the front and the back where it's got points, it's also fairly smooth. It's got kind of an elliptical shape by default. And it has a nice curve here coming around. So it does have fairly smooth surfaces. But let's talk about something you might try to do in order to make a fuselage. Now, I'm going to leave these front and back points, but I'm going to make this front one a little bit smoother, have it come into various changes in oval shape, then come back to a point at the back edge. And we're going to try and make that smooth. Now, the way you do smoothness is skinning and angles. So if you look here on the geometry dialog box, you'll see this skidding tab and this cross-section tab. So point 0, which is this lead one, is a point. The next element out is this one here. Take a look at that. You can see it's an ellipse. Now, ellipses have nice smooth shapes out here. Now, you can play a little bit with the cross-section of these ellipses. So let's talk a little bit about that. So you can make nice smooth shapes using this ellipse. But you can make even more interesting but still smooth shapes using the super ellipse. And I like starting with the super ellipse almost always, just because there's very few times I want an actual elliptical shape on my fuselage. I almost always want something just a little bit different. So there's a height and a width that you can set. So that's overall height, overall width. So let's play that with a little bit. So right now we're turned a little bit 90 degrees because I'm changing height. That looks like it's changing the width. Let's fix that a little bit. There, that's a little bit better. So you can see Z is now going up and down, which is the height. So let's go back and try that again. So you can see I change the height and change the width. But regardless of how much I'm changing it, you can see there's still fairly smooth cross-section here. Now, it's also been always symmetrical as I've been changing this. You can unflag, setting top and bottom to symmetrical. Now we can actually change the top and the bottom a little bit. So we can change where the maximum thickness occurs. Now right now it's halfway between the top and the bottom. Let's move that a little bit. So you can see I can move it down, I can move it up. So for our fuselage, frequently you might want to have that maximum thickness down low a little bit. So it's almost kind of an egg shape now, but it's still pretty smooth, has nice smooth contours. Now this M and N you can also use to change the shape a little bit. So we have M and N for the top, and M and N for the bottom. So let's go ahead and change this bottom a little bit. Now I always have to play around with them just a little bit to figure out what they do, but basically one causes the side to come down a little straighter and the other one causes the bottom to come out a little bit straighter or less straight. So this is where you can lose a little bit of that smoothness. So let's go ahead and play with the M first here on the bottom. So you can see mostly that's playing along with this bottom edge here. So we've made it fairly flat, farther out, and then it curves up. Now actually, that's again a thing that might be nice for a fuselage, make it nice and flat on this bottom. Now let's do N. So you can see N mostly changes how flat this side is out here. So we've extended this out, but you can see we still have fairly nice smooth shapes. Now these aren't necessarily conic shapes like Dan was talking about in the book, but they're still fairly nice smooth shapes. But you can change M and N to where you don't get a smooth shape. Now that's probably okay here on this fuselage, particularly on the top or the bottom, where you might want to have it be a little bit sharper. So let's say for some reason we wanted the top to be just a little bit sharper. Let's go ahead and play with that. So you can see as I change M, instead of being flat like it is here, I can actually make it sharp. So as you can see, using this as super ellipse, you have quite a bit of flexibility on how to make a smooth side, or you can even have a sharp side. And in fact, not just on the top, but here on the side, you can make a sharp side too. But you can use N here, bring it down to a small value, and you can have a sharp side. And in fact, you can actually completely destroy the elliptical shape. And here you can see we've made it convex. So I like the super ellipse. You can do a lot of fun stuff with it. But let's go back to being smooth. So let's crank up M and N. Oh, that's not too bad. So now we've talked about smoothness in the cross section. Let's talk about smoothness in the longitudinal direction. Now that's a little more tricky. Let's get a side view. It's a little easier to see the smoothness on the top and the bottom with the side view. Let's go ahead and offset this just a little bit like you might have on a nose. And an example of that would be like the UWS-4 Ultralight. So we've got the cross section. We're going to raise, using delta Z, we're going to raise that second element up relative to the first. So let's go ahead and raise it up kind of like that. Let's come back here and increase the height of this next one a little bit. So that's element 2. Let's come back here. Let's make it a super ellipse. And let's crank the height on that one up a little bit. And then let's raise it up also. Something like that. Now we're starting to work on the front of our fuselage. Now look at how on this first element and second element, even though we've done some crazy stuff to it here in this profile, it's still trying to make it nice and smooth. Now it's got a conical shape all along here. Now OpenVSP, using its skidding algorithm, which we haven't gotten to yet, but we're just about to, is trying to do its best to make nice and smooth curves in here. Well, let's help it out a little bit. Let's come back here to the nose. And let's tell it we want 90 degrees. Now right now on skidding, if you look at that, you can see this angle right here. This angle is set to 45 degrees, and that's how it's starting out, roughly 45, but then this is so much higher than here that it rapidly curves up. Well, let's make this a little bit smoother here at the front. We're going to do that by changing this to 90 degrees. So there's 90. And there's 90. Now if we had said 0, it'd come right out along this line. Now you can see we have a fairly smooth curve here at the very front. So we're starting at 90 and then we start curving around. Now we really don't like this lip here, this funny shape here. It's more of an S curve. We really would like to have more of a smooth curve coming up. Again, we can do that. Let's come back to skidding. Let's go up to element 1, which is this element here. And again, we have the angle that we can change. Now right now, the angle on that curve is 0. Now we have this check mark here. The left-hand windows over here have to do with the left-hand side or the forward side. The right-hand windows over here or items have to do with the right-hand side. So anytime we have a check mark here, the left and right side will be identical. You can see how it's checked here. This is grayed out. That means you can't set it. You only set it over here, and that ends up setting both sides. Now for this video, we're not going to get into slew. We're going to ignore that for now, and we're going to ignore curvature. So let's play with this angle a little bit. Let's try to make this look a little bit more aerodynamic along here. So I'm going to come up to this slider. So as I play with this slider, looking over there, you can see the angle changing. So there I went too far. Let's come back. And you can go really, really far and get quite a dip in there. But you can see OpenVSP is doing its best to make a nice smooth curve through here. Now it's not necessarily fair, something that we call fair through here, but it's doing its best to make a smooth curve. So it's up to us to make it more fair. So we can do that by going back and playing with the slider, coming back, and by just using our eyeball, we can actually make it fairly fair along here. So right in this area here, between this and this, that looks pretty darn good. Let's do it on the bottom. So right now we have this flag here that says top bottom symmetry. Let's turn that off because it's setting the same angle on the top as we have on the bottom. I don't want that. I want a different angle on the bottom. So we unchecked top bottom symmetry. Now let's play with this angle here until it looks nice and fair coming through here. Okay, that looks pretty good coming through here. Now, until we've seen these angles out here a little bit farther, we really aren't quite certain how we want to do this angle. Let's go ahead and add just a little bit more in here as an example. We don't want to get too far and spend too much time on this, but let's go ahead and make something that's somewhat fuselage shape. So let's go out here to 1, 2, 3, element 3. Go back to cross section. Let's set that to a super ellipse again. Let's set the height a little bit higher. Let's move it back a little bit, a little further back like this. And let's move it up a little bit. I think that's probably enough to finish our example here. We'll have to imagine that we have just a little bit more fuselage back here. So I think having a 0 angle here and a 0 angle here is probably good enough for what we're doing. Let's go ahead and leave it like that. But let's see if we can make this a little more fair coming through this spot here. So let's come back to element 2 and let's work on this angle. So we come back to skidding and we play with that angle. That looks pretty good. Let's do it on the bottom. Uncheck top and bottom. That looks pretty good for now. Now this isn't perfect. In fact, I think I would probably come back and change the angle on one just a little bit more. Flatten it out just a smidge. So as you can tell, I'm just eyeballing how to make this fair along here. Now it's not perfect doing that eyeballing. It's probably not perfectly fair, but it comes pretty darn close. Now you might be wondering here about this middle part here. Well, there's a couple of things we can do to fix this little bit. This will make kind of an odd shape if we imported this into a CAD program and started using it. The way we can fix that is using the skew parameter on the sides. But I said I wasn't going to talk about that. Now, if we want to work on the side, we can do the same thing. So we could do a view from the top. And you can see again, it looks a little bit odd here. Let's go ahead and make this one here a little bit narrower. And then we can work on making it a little more fair, the same way we just did. So for example, we come back here to number 1, go to skidding. Now we're dealing with left and right instead of top and bottom. Now I usually do want left and right to be symmetrical, so I'll leave this checked here. So we'll come to this right side and change that angle. Come back to number 2, let's change that angle. That's pretty close to being fair. So that's how I do fuselages and booms, that sort of thing. Now there's more to it. There's the skew angle and the strength in order to play with how curved these surfaces are. Because right now you see the strength says left to 1, and 1 is a pretty good default. But sometimes you want a little more curvature closer to one side and a little bit flatter on the other side, and that's where strength comes in. But we're not going to do that in this video. I just want to give you a little bit of a taste of what you can do to try to make smooth sides in OpenVSP. Now, if you want to try to make sure that you had conic sections here, you actually could do that. I'm not going to get into the math of it, but by knowing how far back you are in the X direction and how far wide you are, that would give you a coordinate here, and you could actually calculate what the angle should be here. And then you could insert it in the skidding, and you could calculate what the angle should be here in order to get a conic section. Then you could actually have a full conic section coming all the way from front to back. And I might do that at some point. That'd be kind of fun to do. Now we're going to talk about a non-compound curve, where it's a flat wrap. So what is a flat wrap? A flat wrap is a curve that you could actually make with a sheet of paper or something like a sheet of aluminum. So at any point you would pick on the surface. In one direction you should be able to get a perfectly straight line along that sheet, and in the other direction it can be curved. So 90 degrees that it would be curved. So if you want to use sheet aluminum on your airplane and don't want to have to make compound curves with it, because in order to make a compound curve you have to have a lot of skill, like using a shot bag and a soft hammer in order to bend and pound aluminum into the kind of compound shape you want, or you have to use something like an English wheel. And it can take quite a while to gain that skill. But you really don't need any skill if you can do a flat wrap. So Dan talks about some techniques for determining how to draw something like a wing in order to do flat wrap. Now you can also do flat wraps on the fuselage. If you look at the Ultra Cruiser, the Hummel Ultra Cruiser, it does flat wrap sections for the fuselage. Now, being able to do flat wrap correctly is also something that can be really useful for a wing. Now, if you're doing a Hershey bar shaped wing, in other words, the root and the tip both have the same airfoil and the same chord length and no twist, you automatically have a flat wrap. You could wrap aluminum around that airfoil, that wing shape, easily. But what if you have different airfoils on the root and the tip, and or you have some twist? Then it's just a little more difficult, but it can still be done. What you have to do is be careful about the ribs between the root and the tip. Those ribs have to be shaped so that you can still do the flat wrap. And that's what Dan talks about in his book. The method to go through to come up with those intervening airfoil shapes so that you can do a flat wrap. Because if you're not careful and you just draw straight lines linearly from the leading edge to the trailing edge, you may not get a flat wrap. So Dan talks about a really interesting technique to come up with those intermediate airfoils so you can get a flat wrap. So here's a wing I made to try to demonstrate what Dan's talking about in his book. So here's a wing that has an airfoil here at the root that's different than the airfoil out of the tip. And just grossly you can tell that this airfoil has camber to it and this one doesn't. Another change that I made is the maximum thickness of this one up here at the root is up here around 20% of the cord, and the maximum thickness of down here is around 35% of the cord. Now to make ribs along here, for example ribs that might be right here where we have these lines already that OpenVSP put in here, if you just do a straight linear interpolation, for example you draw a line from maybe the 50% cord here to the 50% cord here, and then similarly do it for each other percent coming along here, and then made airfoils there for these intermediate airfoils, and then try to do a flat wrap, you won't get a flat wrap. You'll have some troubles. You get a little bit of buckling and bending in that sheet. Is you look at places on the root airfoil and the tip airfoil that have the same slope. So as an example, the very top of the airfoil, this top surface, if you drew a line tangent to that, where that line is perfectly flat, 0 degrees, and then do it down here, and then draw a line between those two, and then you do the same thing for each angle along here as you go, and then you use those lines to make your intermediate airfoils, then you can have a flat wrap. The 0 degree slope for this airfoil is going to be right about here. Let's just say it's right here at this spot here. The 0 degree slope for this airfoil is back around here about this spot. So let's talk about those spots. So let's follow this line back. So it is not at the same location as this one. So what we would have to do is actually draw a line from here coming across to this location, draw a straight line there. And then you would come back to where you have maybe 5 degrees here, and 5 degrees back here, you draw a straight line. And then use those lines to make your intermediate airfoils. Now at the moment, I don't know of a way to make OpenVSP do that. So if I were to have a wing that had twist in it and or different airfoils, then we'll have to use Dan's method to come up with the intermediate airfoils. But fortunately for the UWS-4, I'm using the same airfoil at the root as I am out at the tip, and I'm not doing any twist to the wing. So I don't have to worry about dealing with flat wraps. I'll have it automatically. Another thing that Dan talks about is fillets. So how would you draw or design fillets in your drawings? Now, just a reminder, a fillet is kind of a curved section between something like the wing and the fuselage. Let's say you had a fuselage here that goes straight up and down. You have a wing coming out here to the right. Down here in this corner where they intersect, you would have a curved, smooth section in here, and that you would call that a fillet. And real briefly, we've talked about fillets before, or indirectly, we've actually talked about interference drag before, and how you can use fillets to reduce interference drag where you have a wing and a fuselage come together. And that's one of the main reasons for fillets, is to reduce interference drag. And Dan talks a little bit more about that in the book. But more importantly, we're talking about how to design those fillets and then how to draw it. Now generally, your fillet is going to be circular shaped. It's kind of a circular arc. And then the arc is going to intersect the wing at a tangent point and a fuselage at a tangent point. And when I'm saying tangent to the circle. Now that circle, you want to be perpendicular to the wing surface. And what he means that is, for example, at the very top of the wing, your circle will be up and down, straight up and down, but out at the leading edge, your circle will be flat. So the circle, as it's coming around the wing, will start changing angle to match the surface of the wing and still be perpendicular to it. Now the next question is, how big should that arc be, the radius of that arc? And Dan's saying, well, you start with 10% of the root chord of the wing. So the chord of the wing near the fuselage, 10% of that length would be the radius for your fillet. That could be a pretty large radius. On the UWS-4 ultralight airplane, if I remember correctly, our chord is 54 inches, so 10% of that would be 5.5 inches. So that would be the radius of the fillet we want to use, using Dan's recommendation. And then he says, as you're approaching the trailing edge of the wing, you would probably want to make that radius larger, although he doesn't really give guidance on that. And as a modification to that, he's saying some airplanes that would actually start the fillet at the maximum thickness of the wing, where it's meeting the fuselage, and so that would be a 0 radius, and then you start increasing that radius of the fillet as you move backwards on the wing. Now talking about fillets on the UWS-4, I'm thinking that what I'm going to do is I want to find out how effective fillets would be. So I think on the very first iteration of the UWS-4, I'm going to leave fillets off. So we're going to have some nasty little angles back there toward the back edge of the fuselage and the back edge of the boom, or at least where the boom is crossing the back edge of the wing, because that's going to be even worse than a 90-degree angle. It's going to be a little bit sharper than that. So I would guess we're going to get quite a bit of interference drag. So I want to go through all the flight testing with the airplane without fillets on the wing. I want to get some performance numbers, try to get some drag numbers, and then come back and add fillets, and then do all that performance testing again and find out what the difference is. Would fillets really make a significant difference on this airplane? Because fillets will add some weight. And if there's almost no drag difference, then fillets just aren't worth it. But I'm pretty sure fillets will make a significant difference. So we'll take a look at that. That'll be a fun experiment to do. Now the last section that Dan has in his book is measure what you drew. In other words, after you've drawn it out, you have to actually start doing some measurements to figure out some really important data on the airplane. And one of those things is going to be the wetted area of the various parts of the wing. So the wetted area would be something like, let's say your wing is solid on the inside, you don't have any voids inside. And if you dunked it in water, then any part of the airplane that will be wet, that would be the wetted area. Now, wetted area can be a little bit difficult to calculate, especially if you've done hand drawings. So he came up with some good ways to estimate what that wetted area would be. So you would have to first figure out what the exposed area of your wing is if you want to try to calculate the wetted area of your wing. And that's not too hard to do. That's basically the planform area of your wing that you can see when you're looking down from the top. Now you still might have to do some estimations, but you should be able to do a fairly accurate estimation. But trying to do wetted area from that would be really difficult. So using this equation, where this is the thickness ratio of the wing, so how thick it is divided by the chord length, and then multiplying that by 0.52, adding this little constant here, about 1.9 or 2.0, and then multiplying that by the surface area, and then that will give you the wetted area of your wing. And you can also use that for your vertical and horizontal tail. Now fuselage, that one's even more difficult to estimate, but he's got an equation for that too. So looking at the area of the wing as you're looking at it from the top, so basically the profile from the top, and then also the area looking at it from the sides, the profile from the side. You add those two together, divide by 2, and then multiply by this constant. Now if you have a rectangular fuselage, you actually have to go a little bit larger. The wetted area would be larger. So you would actually, instead of 3.4, you'd multiply by 4. Now if it's more circular, then you multiply by pi, so 3.14. Now if it's a strange shape, like I've done on the UWS-4, I've got some very odd shapes as you move along that fuselage, then you really need to stick with this 3.4. But OpenVSP has some pretty nice utilities for doing these calculations for you. Well, what does OpenVSP provide us in order to figure out wetted area? Well, I think it's pretty neat because you can not only get wetted area, you can also get the parasitic drag. So I've brought up the wing and fuselage, the pod for the UWS-4. We can come up here under Analysis, go to this Comp Geometry. Now I've already done it once, but we'll go ahead and do it again. So for the objects that are shown, so that's what I've selected here. I've unselected the subsurfaces because I don't want to have the flaps and ailerons separate, although there certainly isn't anything wrong doing that, but I want to simplify this just a little bit. I'm going to say execute. So let's come up with a degenerate geometry here. So the right wing, left wing, and the fuselage. And you might be able to tell here, but it actually has cut out the wing area where the fuselage is. So we actually will get the exposed wetted area of the wing. It's not going to do the entire wing. Now if I really want to do this legitimately to get real numbers, I have to include the booms because the booms intersect the wing too, but I wanted to simplify this a little bit. Now let's come over here and look at what we've got here in this window. So if we come up here and look here, you can see wet area. So we can get the wetted area for the wing. So that's this one here. That's 258 square feet. And we can get the wetted area for the pod. So that's 67 square feet. And guess what? We can get the volume. So we have 71 cubic feet. And for the pod, we have 37, almost 38 cubic feet. So that's something that's really nice about OpenVSP. You don't have to have a rough estimate that you would get using Dan's equations, although I'm pretty sure those are perfectly good, but you can actually get much more accurate ones. So that's a pretty neat facility that OpenVSP has. What are we going to talk about in our next video? Well, let's go to the next chapter in Dan's book. And the next chapter in Dan's book, chapter 6, talks about safety. And the two main things he's going to talk about there are seat belts and flutter. So we're going to deal with those two issues for the UWS-4 ultralight airplane. That's it for now. Thanks for watching, guys. Until next time.